think it costs Boeing to develop that new aircraft to where it's certified, ready to sell, and carry passengers? Can you guess? Start with B.
1 billion?
1 billion? 1 billion? Yeah.
Sorry, I couldn't hear you.
So how much you think it costs Boeing to develop and certify the 787? Start with B. 15, 10. 10 billions. 10 years ago, if you check, even now, they check the stock price of Boeing and multiply by the outstanding stock. What does that mean? You know stock market, right?
It means their total capital.
That means the total capital of the company. Guess how much it is at that time?
5 billion.
No, 50 billion. So what does that mean to you? Let's say this is your own personal finance. What are you gambling? You're gambling the future of the company. 20%. If you fail, bye-bye. You're gone. And companies like Lockheed Martin, who used to be commercial, they have L-1011 airplane, and McDonnell Douglas, gone. Gone. Okay? So point number 2, the engine out in the hallway. We have visitor from Rolls-Royce today, so I may have to dash out just a little early, not much. That engine has engine problem. It's not disclosed, but it's a problem. Guess how much it costs to fix it?
10 billion.
Not that much, but start with B. A lot of money. A lot of money. I won't say how much, but just a lot of money. Once something is built, trying to fix it is just cost prohibitive, right? So what does that have to do with dimensional analysis? So you don't build an airplane on a golf course and say, I'm going to gamble the future of the company. No, it's just not the way it works. So you try to do a lot of testing. And dimensional analysis is where you can reduce the complexity of a given problem. And that's, we're going to do a deep dive, not for an airplane or an engine, but for a hole in the pipe. And see what this means by reducing the complexity and using a grouping technique. So at the end of the day, I don't have to do as much testing as I would have otherwise. So people like Pratt & Whitney, they will build component of the engine. So is Rolls-Royce. For example, that big fan at the very front section of the engine that's like about a little less than 10-foot diameter. They would test a scale model as little as 2-foot diameter, this big, in a test cell, and just to see if it works. And guess how much it costs just to do that test?
$10,000.
$10,000. How about $10 million? And that was whole number. So they're expensive. So what we are tasked to do as an engineer is to ask ourselves, what can I do to do a small-scale experiment, like the wind tunnel in the parking lot out of Randolph? And some of you are from Hampton, wind tunnel at NASA. We're going to talk about that maybe in 2 lectures. What can I do to make my experiment realistic, meaning that it represents the real engineering physics, all right? And you learn that you can't always match all the parameters. And that's where the engineering judgment come in. You make a guess, right? You do the best test you can do that you can afford, because you're not going to build a full-size 787 and start flying it, right? You're going to test it in the wind tunnel and then get the data. How do you know the data is right? That's what we're dealing with in this next lecture, okay? So the test has been graded. We will return that next time, but you see your grade on Cabot. The average is 86, on the high side, but that's fine. So some of the problem test 1 is on problem 2. Some of you, for a reason I did not understand, draw a control volume that encompasses the faucet. What's wrong with that? I mean, there's something wrong with it. It's just, this is what I asked. So when you draw the control volume on the faucet, what happened? What are you introducing that is not asked in the problem statement? Well, you have included force on the faucet, which I don't care, and I'm not asking that. Okay? So that's things that you don't want to complicate yourself by choosing the control volume, and the rest of you should know how to draw the control volume. and I didn't draw the diagram right. It's a big secret. Okay, so, if you have any question on the answer to test one, see Mike in the office hour, we'll go over the test with you. Quiz 4 has not been graded yet, we'll return it next Tuesday also. And I will go over the answer, which is pretty simple, it's just a walk in the park, I hope. The unit for wall V squared in SI, and show the intermediate step, which I like to see. And you know it's the same as pressure, so it has to be in Pascal in SI unit. Do I have to go through that? Okay. Half V squared divided by G. What's the unit of that? And how do you see that from the given equation? What you do is take the equation and divide it by what? In order to get the unit of only V squared divided by G, what would you divide this equation by? Rho G. So all I'm saying is, all this can be done by inspection. You can obviously work out the unit, that may be even faster in this case. But my emphasis here is that they all have the same unit, and what you see here, this term must be the unit of height. We call it the head. So what do you call this term? Head. What kind of head? Either velocity head or dynamic head. Instead of pressure, we now have the unit of length, height. Rho G H, the H, 760 millimeter of mercury. That translates to pressure. So that head will be used in about a month when we talk about, or less than that, two, 3 lectures when we talk about energy equation. Any question on that? Part 3, if there's heat transfer and work done, can I still use Bernoulli? The answer is yes. Why yes? Why yes? Because Bernoulli had nothing to do with energy equation. They're decoupled, and when there's heat transfer, as long as density remains constant, all the 4 assumptions are met, you can use Bernoulli. And even there's work done, same. Okay? So the answer is true. And the 4th question is just the differential equation of motion for frictionless flow. We call it Euler equation of motion. So just a very simple quiz, nothing to it. So what I want to do is to prepare you for the pipe flow, which is pretty involved and pretty deep. I just want to revisit by example of this mass, length, and time quantity, which in this case, just as an example, in dimensional analysis, you're going to have to express all the engineering quantities, viscosity, pressure, force, etc., all in terms of mass, length, and time. So for one more time, as an example, in the English unit, I'm going to work out this equation called term 1, 2, and 3 to reduce it to the fundamental mass, length, and time unit. So starting from term 1, which is pressure, time force divided by what? Time force divided by inches squared, that's pressure. In the denominator, I have density, which is pound mass. In this case, I use inches cubed. So this is very straightforward. Instead of using mass, length, and time, I just want to work it in English unit for one and only one reason. What am I missing? G sub C. Yeah, very good. G sub C. Which will allow me to essentially convert this unit feet square per second square. That's the easy part. Let me stop and let you catch up. That's the easy part. The hard part is, can someone give me a physical interpretation of what this term of velocity square really mean physically? Yes?
Is it the kinetic energy per unit mass?
Very good. Very well said. So term 2, I will work that through, and that's very simple because of the unit of velocity square is simply feet square per second square. So the way I would answer the question I posted is, you remember from freshman physics, half mv squared is what? Kinetic energy, right? So v squared would be what?
Kinetic energy over 1/2.
Kinetic energy divided by what? You want to go from this to this. The half is inconsequential because I'm only looking at the unit. So divided by mass. So different formulation of the Bernoulli equation have different physical interpretation. So now I'm looking at each term as in energy, energy per unit mass. So this formulation have a different interpretation, right? And the fact I use term energy doesn't imply that a Bernoulli is an energy equation. It's just a convenient way to write the equation and hope to interpret the physics of that. And the last term, obviously, will have the same unit. So this is the last example I will draw on in terms of working units of mass, length, and time. Yes?
So if this is energy per mass and you have flow basically like we had in the homework from one point to another and you're adding energy, do you add that energy term?
No, I want to emphasize, when you deal with Bernoulli as it is here, I don't want you to think energy equation, okay? I'm using this, and it's very dangerous, I'm using that just to illustrate the term, the quantity, like v squared, or dz, or pressure divided by density. It can be looked at as a quantity of energy per unit mass. I'm not implying the Bernoulli equation is the energy equation. You will see in about 2-3 lectures when I introduce the energy equation, then we talk about energy. How's that? It's very dangerous. I wish I actually would hold this discussion until I introduce the energy equation, but I hope I'm making myself clear. Bernoulli is nothing to do with energy. Yes?
Will we go over special problem 1 later?
Yes, we will. That is part of the agenda. And I do want to cover the new material first. Okay? Fair enough? All right, good. Okay, now let's do our core problem for today, which is the flow in the pipe. So anyone heard of this company?
Yeah.
Where are they located?
Wisconsin.
No, there's branches in South Carolina or North Carolina. I forgot. What do they make?
Air tools.
They also make pump. Okay, so Ingersoll Rand is a company that hired quite a few hookies. And pretend you are one of the engineers who work for this company that make, say, water pump. Right, that can or any fluid pump that can handle water or gasoline. And you are tasked with estimating the frictional loss for flow in a pipe. So I'm going to give you a section of the pipe, diameter is D, the length is L, I have flow going from left to right, and friction is included. My task as an engineer is to estimate the pressure drop. Pressure drop is due to the friction in the pipe as the retarding force, so you have to provide higher pressure at point 1 to push the flow out at point 2. So a couple of assumptions. Steady, which nothing changed in time, so what comes in must exit on the right. Constant density. And the pipe for now is horizontal. I don't want to deal with gravity yet, and that can be included later. So then, a couple other applications of this type of problem will be water supply in your home. From the municipal of 120 psi of water supply, is that enough to pump water to the 3rd floor of your building? Or in the dormitory, 10 floor up? Or airflow in, say, a tunnel. The Hampton Road tunnel, you have to have fans that drive air through the tunnel so that the air is not too polluted. What size fan do I need to pump that air through? So those are big scale type fluid flow. The smaller one will be as simple as if I have a drinking straw and I'm blowing through that drinking straw and pushing air from my mouth through the straw, and there will be viscous effect. How hard do I have to push to get the air out? And even on a smaller scale is your needle or a syringe in the doctor's office, right? Injecting fluid into your body, tiny capillary tube, how much pressure I need to get that drop into your body. All those involve flow in the pipe. And what we will do is use dimensional analysis to see if there's a way I can simplify this problem with the objective, when I'm done, of coming with a way to estimate the pressure drop. So that my customer know for a given flow problem, pumping gasoline for the Alaska pipeline, over 10 miles. How big a pump they need? What is the horsepower required? So as a mechanical engineer, my task is to look at this flow problem and come up with an estimate of the pressure drop. Now, the exact formula that estimates the pressure drop will be chapter 8, flow in the pipe. Right now, we are more concerned with, can I simplify this problem by reducing the number of variables, reduce the complexity, so that I have a much simpler experiment to perform. And that's our goal. So at the outset, step 1, I'm going to lay it out in different steps for you to follow. As an engineer, you do have to have some insight and tell me what are the variables. In other words, what are the things that will affect the pressure drop? Any guesses from your intuition? Temperature turned out not to be a first order effect. And I'll answer that later on after we get all the variables out.
Velocity.
Velocity is first order because how fast I pump the flow will dictate how much frictional loss I have. Length, very good. The longer the pipe, intuitively you think I would have more pressure drop, and it's actually linear. And we'll look at that in chapter 8. But right now I just want to ask myself, what are the variables, what are the parameters that will affect this pressure drop? Viscosity, very good. Because I do need to know whether it's oil that I'm pumping, or water, or air. And if it's oil, what kind of oil? There's different type of viscosity for different oil, as you know. What else? Diameter, yeah, very good. Small capillary tube is very different than a 10-foot diameter hydraulic pipe that is used, say, in Hoover Dam, which is out in Arizona, or at Crater Lake or Smith Mountain Lake. Size matters. What else? No, that's it?
Density?
Density, very good. Density. Absolutely. Again, air, water, oil, water, different density. The last one is not obvious. E. Anyone remember that from your 21-24?
Roughness?
Roughness, very good. Roughness. Friction is along the inside wall of the pipe, so if the pipe is not smooth, but over time, in a steam power plant that's 30 years old, and the pipe get rusted, it affects the pressure drop. And so those are what we call on the right-hand side independent. Where? Because each one of those is independent of each other, and if I change one of them, it will change the pressure on the left-hand side, which I will call the dependent variables. While we are using this pipe for as one example, there are others and homework that will follow, but the scheme is the same. Step one is just ask, what are the parameters that will change my so-called dependent variables? So this is purely physical insight, you know. You don't have that insight, then you cannot go on. But luckily in fluid, all this problem has been worked out. Flow on an airfoil, flow around a sphere like a baseball, all have been tackled before. So it become, after a few set of homework, become repetitive. And we do know what are the independent variables that will affect the problem. Any questions so far? So I'm going to jump to the answer. So there's a step here that will take me about half hour to fill in. And part of that is the homework. So let me go over the assignment, which I didn't. Reading is on dimensional analysis, session 4 and 5. Homework is about 2 hours. The first two, this is what now? Oh, so Mike will post that problem statement for you right after class from the older edition. And then they're all the same, but one is in the new edition that you have, the other one is posted. They are very simple introductory problem relating to mass length and time. The other one is in class, which I will tell you momentarily what I would like you to do. So instead of going through the math and get very in the detail, what we want to do is actually jump to the answer so you can appreciate what is meant by reducing the complexity or reducing the variables and simplifying the problem as such. So let's say we are the engineer at Ingersoll Rand, and I'm trying to help my customer decide what kind of pipe, what kind of pump, what size pump I needed for different applications. And as such, my boss tasked me to do a series of experiments of which you're given a fixed pipe of a given length, given build, given diameter, given roughness, etc., etc. So those three parameters are fixed. How long, the diameter, and the roughness. So with that, I'm going to go into my lab and do a series of experiments of which I'm measuring my pressure drop from 1 to 2. I don't know whether it's an electrical problem or mechanical problem, or this interference due to the microphone. So with the fixed pipe, I have taken out 3 of the variables on the right-hand side from my function, meaning they're fixed and not changing. And all I'm now left to do is to find out how the pressure will change when I change the velocity, like pumping the fluid faster, or how the pressure may change when I change the fluid. And I'm tasked to do this pressure drop test for 3 different fluids: air, and then water, and then oil. Air is the easiest one because it's less messy, right? So that's the one I start first. And my experiment just consists of measuring the pressure at 1 and 2 at different flow rates. So I can change the velocity. That's a fairly simple experiment. I think you may have done some of this, or you will do some of this in your MB lab. And from that, I measure a series of experimental data, of which is based on the density and viscosity of air. So, any question on how this experiment is performed? Pretty straightforward, pretty simple. Some of my students do that in the lab all the time, graduate students. Very easy type experiment to perform. So the next step then is change the fluid to water. Similar axis of pressure change, which is my dependent variable, and different flow rates or velocity in this pipe. So for air, now water, I have a different viscosity and a different density. I would yet have now another curve. And that's for water. In reference to the previous one, if I plot the data on the same plot, you can compare the difference in pressure drop at the same velocity due to the fact it's a different fluid. So done with the second experiment, and I'm doing the third one, which is just a repetition. So I will change the fluid now to oil. Delta P again, viscosity and density of oil, which is different from that of water, and different from that of air. So one more time, I get a third relationship of pressure drop versus that of velocity. Okay? So far so good? Can you see yourself doing this experiment? Relatively straightforward and simple. If I overlay the 2 previous set of experiment for water and then for air, they may look like this. So I've done 3 times a very similar experiment. Finish. So what does this have to do with dimensional analysis? What I mean by reducing the complexity and the number of variables of the experiment? Well, what that translates to is there a way for me to plot the same data differently? Instead of actual pressure in Pascal or PSI, I want to plot it in terms of a dimensionless. Pressure. What is to be determined? Instead of velocity, can I plot it in terms of a dimensionless velocity? Again, what it looked like to be determined. Such that all 3 graphs, if I take that set of 3 data and plot it in terms of air, now in the dimensionless form, they will look like this. second set of data, which is water. Again, in dimensionless form, not in velocity in feet per second, but rather this dimensionless perimeter yet to be determined. They collapse. They fell on top of each other. Perfect. Yes?
So how can pressure and velocity like be dimensionless?
Okay, that is what we call the grouping technique, which is something we will do in this dot, dot, dot. But since you asked, let me ask you, anyone want to make a very, very intelligent guess of how I may make a dimensionless pressure, which is something you have seen in a different form in 2124? Yes?
Oh, well, I'm just gonna talk about the graph in general, but then.
Okay, we can come to that later. But let's just ask ourselves, what do you think is the, by inspection, can someone tell me how I may non-dimensionalize a pressure? Yeah? Yes?
You could divide like the change in pressure by 1/2 rho v squared, because then you have the same units.
That's exactly what we will do. Right? So this so-called dimensionless pressure is delta P. My data on the left, which I measure in Pascal or PSI, I want to divide that by something so to make it dimensionless. And the most convenient perimeter which you have seen based on Bernoulli is dynamic pressure, rho v squared. And that's what we do. And that's what we call grouping. Because I succeeded in taking a physical quantity of pressure and make it dimensionless. Do you understand what we have done on the y-axis? Yes?
If it's dimensionless, how do you call it dimensionless pressure or dimensionless velocity?
It's dimensionless because this quantity, delta P divided by rho v squared, has what unit? Has what unit? Pascal? No. Delta P divided by rho v squared is what unit? Unitness. It's dimensionless, but no unit. That's what you did in SP1, right? This quantity has no unit whatsoever. And hence we call it the dimensionless perimeter. Do you get it? This, in a moment, we got a pi term. This is pi 1. One of the circle dimensionless perimeter that we are going after in this dot, dot, dot. So when I'm done, what appeared to be more complex a problem has been reduced. Yes?
So physically and intuitively, what is the overlaying of the air and water graph telling you, like the lines?
So why would the data collapse? Is that what you're asking?
Yeah.
It turns out when we will look at in a month the differential equation of motion for pulling the pipe with viscosity, that's called the Navier-Stokes equation. That's the holy grail of all the problem in fluid. When we do that, if I make that equation dimensionless, all those perimeter will come out. And the physics become independent of the fluid. Okay? It's only a function of those dimensionless perimeter. And that's how the data can be collapsed in the way that I'm trying to describe to you. All right? Any guesses as to what's the x-axis that will give you a dimensionless velocity, which is something you've seen in 2124? Anyone else? No clue? How many dimensionless perimeter you have learned in 2124, especially in pipe flow? The Reynolds number. The Reynolds number. So this so-called dimensionless velocity will actually be a Reynolds number. And how is that defined? Anyone remember? No? Reynolds number? Yes?
And the
Diameter, yeah, very good. What's the denominator? Viscosity, yeah, you got it. So if I plot the data in this dimensionless form, the third and the last data of oil will all collapse into one single curve. Now I can answer other questions. What was your question?
Oh, well, I was just gonna say, when it all collapses down together, I mean, you kinda covered it, it
Yes.
just means that it's all gonna react the same.
They don't all behave the same way, independent of the fluid.
Okay,
That's the beauty of what we have done.
because then the slope, cause like, if you look at the other ones, the slope's pretty much the same, so is that pretty much like what we're comparing is like the slope of each?
It's not just the slope, because it is all normalized by the corresponding density and velocity. Each individual line, I just make it casually, they may not follow the same slope.
Okay,
No, they don't. I don't even pay attention to that. And it's inconsequential how each of those three behave individually on the far left. When you plot them in terms of this dimensionless term, we'll create only one and one graph. Okay? And this is also a pi, we call it pi 2. So what's the big deal? So what? And all this 20 minutes spent on this, what? Are you excited? No, you're not. You don't even know where we're going. So if you are an engineer working for ASORAM and you're tasked to do this problem, what do you do to cheat? What do you do to cut down your work? And then you can tell your boss, oh, I worked the weekend to get all the data, but actually you are going to a football game. Right? How do you cheat? What would you do? Yes?
make it dimensionless and solve it for any.
Make it dimensionless. I'm just going to test air and air only because it's easiest. It's less messy. And I'm going to plot the data dimensionlessly, like this. And everything will follow this graph based on dimensional analysis. So that your customer will use this graph universally, because he or she may not be working with air, they may be working on refining crude oil for Exxon. But what they can do is tell me the Reynolds number you are at for this particular problem, how fast you're pumping the flow, what crude oil, what viscosity, and what density, and I calculate the Reynolds number, bam, I'm here. And I'm going to look at cost. And uniquely and unambiguously, meaning there's only one and one answer, I know the pressure drop. Dimensionlessly. And to get the actual delta P in PSI, I multiply that by rho V squared. And then I can size the pump. On and on. And someone else can use it for a steam power plant where you pump water in a condenser. Same. Calculate the dimensionless Reynolds number. It tells you where you are on this map. It tells you how much pressure drop. Yeah?
So, when we talk about like turbines and stuff, you said like, this is a good like back the napkin kind of calculation, but this isn't exactly what happens, you know, like you don't get paid $7,000 a year to do that. Like, is this what's actually used, or is this like a good model, like a good intro?
I don't understand your question. This is what people do, this is what my graduate students do every day for
Okay. So this
companies
is
like
what they
Pratt
act
Whitney and
like-
GE.
Okay.
So in GE, you build a new design, you use some very sophisticated computer simulation, and you design a new turbine blade. But you don't know if it works as intended. This is all a computer simulation. What are you going to do to find out? Well, one way is you're going to build a $500 million engine, you test it, and then you get FAA certification. But if you fail, your company will go down the toilet. So they may come to Virginia Tech and say, well, can you do a simulated test in your wind tunnel in the basement of Randolph and get me some data so I can compare with my numerical simulation? And that's a different problem, but all based on dimensional analysis. So they're a classic problem like a pipe flow full of airfoil, full of a pump, which you all will have homework to deal with to get you oriented But in real life, people do that for a living. Right? So that small budget test will allow them to screen a different design, and they pick the best one. And then they go on to a more expensive $10 billion or $100 million test at the engine manufacturers. Does that make sense to you? Is that what you're asking? I'm not even sure what you're asking.
Yeah, that makes sense.
Okay. So yeah, this introductory level, yeah, you're not going to invent anything new, but this is the foundation. This is just the very first step of what we meant by reducing the complexity of the experiment. Right? So you don't always build a full-size airplane or engine to test it. You build a very inexpensive subscale. But how do I know my experiment is correct? Okay, those will be addressed later. So this Python is very classical. It's a very good foundation to illustrate all this ... all right, which we will dive in now. But do you see what we had accomplished? Which is very significant because I can make my life a whole lot simpler by looking at dimensionless perimeters instead of actual physical quantities. All right? So any other questions before I go on? So this is step one, is identify those variables. Now we're going to piecewise find the dimensionless pairing or parameters. And that gets pretty involved. So in the next 20 minutes, my task and my objective is to, how am I going to find those Reynolds number? Or how do I find that dimensionless pressure? If I have a new problem that's non-traditional, how do I know how to solve that problem? So let's start over here. Let me take a 2 minutes break just to clear the board. Yeah.
So with this specific example, something that would have otherwise taken like weeks to do can take you 5 minutes if you can find the Reynolds number?
Sort of.
Okay.
Yeah, Thomas. You like Thomas? Thomas. Tommy. I usually pass back. Really, I was not supposed to get that out. At least yet. Thank you, sir. Huh? You'll be just your answer sheet guy, not the questions.
So let's continue. Some of the discussion that follows is a little abstract. So I hope this example will help you to understand what is to be done. So step 2 is actually some reading that you already have from the last assignment. That is, you should have read something called the pi theorem. I won't divide that in class. It's dry and it's not something that you cannot read by yourself. But what it is a theorem that at the end of the day, it simply tells us one number. One number only. And that number represents the number of dimensionless groups you expect to have for this given problem. Let me be more specific. So first I have to identify the total number of variables for a given problem. So for this PyFlow, total, meaning dependent, the left-hand side, and the independent variables. The dependent variable is always one. And for this problem, how many independent variables on the right-hand side? 6. And in the text, we call them the Q. So this first on the left is Q1, meaning that I may have a different problem. Could be an airfoil, could be a pump, could be a turbine. And I'm doing a dimensional analysis on that. And the term on the left, the so-called dependent variable is my first Q. The remaining one is Q1 to 7. So the Q is just a general type formulation. It's not problem dependent. And that just make it more applicable for other fluid applications. So I have now for this problem, the number of variables we call the N is 7. And the pi theorem simply tells us